Hey everyone, good afternoon. Thanks for joining today. My name is Omer Goldberg and I'm the founder and CEO of Chaos Labs. And today we're going to talk about modeling risk and security for cross-chain bridges. So let's get into it. I'll start by sharing my screen. There we go. Nice. All right. So before we get started, just a few words about Chaos Labs. Chaos Labs is a cloud platform that specializes in agent-based simulations. Our main focus is running agent-based simulations to test, to confirm and verify the economic security of DeFi protocols. The way it works is you log on to our cloud. We already have a catalog of agent-based simulations that interface with various popular protocols. You can also create your own if your protocol is kind of niche or novel in any way, shape, or form. And we basically fork the blockchains that we support, which are currently Ethereum, Polygon, Avalanche, and soon supporting Near and Terra as well. And our agents talk directly to your smart contracts in a fork environment in the same way that they're going to be called in production. In addition to the agents that we provide, we also have a catalog of scenarios. These are more like macro changes to the blockchain environment. So some of the kind of features that we already support publicly are the ability to manipulate and control the return value of Chainlink oracles. This week, we're also going to support the same thing for Uniswap, time-weighted average price oracles. And this is critical for unlocking a bunch of testing kind of cases for your DeFi protocol. So you can imagine if you're a lending protocol and you want to test that you stay solvent in kind of rough market conditions, within our simulator, you can drop oracle prices for collateral assets and see that your liquidation mechanics work properly. Lastly, our simulation infrastructure also supports the ability to kind of optimize and test how you tweak different parameters for your protocol. So whether it's liquidity incentives or interest rates for lenders or borrowers, we can run thousands of simulation and show you with statistical significance how these things play out given different market conditions. Lastly, everything is in the cloud, so we can connect this to your GitHub, your Bitbucket, whatever source control you're using in order to kind of write code, have these tests run in an automated fashion and catch regressions as they happen in real time. Now for our talk. Before we talk about modeling risk, let's understand what a cross-chain bridge actually is. So blockchains inherently are closed networks. So for example, the Bitcoin blockchain doesn't know about Ethereum, and Ethereum certainly doesn't know about Bitcoin. So bridges allow us to communicate between different blockchains, and this opens a whole world of opportunity. Let's drill that down a bit. What kind of opportunity are we talking about? Or more specifically, what problems do cross-chain bridges address? So kind of flexible communication opens up the door for a lot of different things. The first thing is interoperability. So we have amazing application that sits on blockchain A and an additional amazing application that sits on blockchain B. Before, or in a world without bridges, are completely fragmented it with no opportunity to kind of talk or to communicate with each other. Via bridges, we can now support kind of the transfer of arbitrary data or messages between both bridges, kind of really enlarging kind of the world of interactions and things that users can do when participating in different blockchain protocols or applications. Capital efficiency. So currently we have like a bunch of layer 1s and layer 2s, and all of them have liquidity locked up, whether it's obviously kind of the Bitcoin blockchain, Ethereum, Terra, Avalanche. Each of them have hundreds of millions of dollars of liquidity locked up. And currently, or in a world without bridges, it's completely siloed. So with bridges, this allows us now to transport liquidity to where it's needed, therefore increasing the overall capital efficiency of the crypto world in whole. Lastly, improved UX. Currently, kind of moving and kind of bridging and minting kind of assets on various chains is a pretty kind of clunky experience, but it's one that users are willing to do in order to achieve this interoperability. In the future, we think that like this is going to become a much smoother experience, and users will be able to kind of freely move their crypto assets across different blockchains in a really nice way. Overall, kind of just opening up the world of crypto to them and improving the overall user experience. Cool. So there are a couple of different ways that we can view actually this whole world of bridges. The first way that we're going to look at it is kind of from the perspective of the user. So from the perspective of the user, it can be broken down into kind of several different subsets or vectors. The first one is asset specific. So you can have a bridge that's specific for one or two type of assets. One example of that is a Bitcoin bridge, right? Bitcoin Ethereum bridge brings Bitcoin into Ethereum. And then also kind of the reverse way when users want to kind of bridge their Bitcoin back to the Bitcoin blockchain, and it's specific to a certain asset. Some bridges are specific to a chain. So you can imagine that kind of like the bridge that kind of powers the connectivity between Near and Ethereum, the Rainbow Bridge, that is specific to Near and Ethereum and currently doesn't support other type of blockchains. We have application specific. So we have specific applications that support their own bridge out of the box. One of those applications, for example, is Anyswap. And generalized. When we're talking about generalized types of bridges, these are more like communication protocols. So if you're thinking of kind of a classic kind of networking, it's similar to that. And their job is basically to serve as a message bus. They transport arbitrary data back and forth. And what they promise us is that the data is valid, has not been tampered with, and is something that the client or the receiving end can trust. So let's kind of visualize the breakdown that we just did. Asset specific. So we have TBTC. This is bridging Bitcoin from the Bitcoin blockchain to the Ethereum blockchain, specific for kind of Bitcoin and Ethereum. We have chain specific. So we have like the Avalanche bridge, which supports bridging assets from multiple blockchains. We have application specific, like we said here. We have Anyswap, Chainflip, Ren as well, and Thorchain that basically all have kind of like their own bridges out of the box that they've built, and then they can maintain and kind of always improve. And we have generalized, so kind of the most, I think, popular implementation of a generalized bridge that we're starting to see is maybe Chainlink CCIP. It's still early on, but a lot of interesting things being built around that. Of course, Layer 0, very, very strong team and very interesting project. And we're excited to see where this goes. All right. So we're talking about kind of mitigating risk, security, reliability of bridges. But before we get into the kind of the thick of things, why should we even care? So there's good reason to care. If you're using bridges to transport your crypto assets to different blockchains, there's a lot of things that happen under the hood. Depending on the kind of bridge that we use, which we'll get into in a second, there's kind of a lot of trust, there's a lot of danger and risk. And it's enough that usually one or two things go wrong for you to get completely wrecked. So this is good reason to care, because potentially all of your funds are in jeopardy when you're basically executing on these cross-chain swaps or transfers. All right. So we looked at how users might view bridges. So they might associate a specific bridge with Anyswap or with Thorchain or to a specific blockchain. But at Chaos Labs, we kind of take a step back. And the way we like to kind of define criteria is by architecture. Because oftentimes the architecture is going to dictate the type of measures and testing that we want to do to ensure kind of the security, quality, and reliability of the bridge. So for us, we look at kind of different things, not in any specific order. If I had to, I would say security is on the top. But we also look at latency, complexity. So how hard is it kind of to implement this bridge? How hard is it to build it? How hard is it to maintain it? Because complexity is obviously like a huge source of bugs. As we jump into the most recent ones, you're going to see that the more complex these kind of pieces of software are, oftentimes the kind of attack surface is larger, which kind of, ends up in more attacks and hacks and exploits. Overhead, so it might be actually that it's not that complex to kind of create, but there's actually a lot of orchestration that needs to happen, and it's a complex kind of journey to get these bridges live. And reusability. So is this kind of bridge super specific to two assets? Does it just mint and lock and kind of release and burn? Or is it general purpose? Can I transport like different types of data, different types of messages? So overall, these are the things that kind of we look at when we're surveying bridges and assessing risk. And for that, here's another visualization which we found. By the way, I highly recommend kind of checking out this link at the bottom. It summarizes the things in a pretty nice way. So this is kind of the additional way that we want to look at it. is not just kind of like in those 5 components which we just mentioned. It's actually like in what is the underlying architecture of the bridge, because that oftentimes speaks and informs what we see here. So let's look at this kind of broadly, and we're going to dive deeper into it as we go forward. External validators and federations. These are kind of the most popular bridges, simply because they're the easiest to kind of implement. They're easy to implement because they're not completely decentralized. So we have authorities or kind of decentralized entities. In this case, they're called validators or federations, which we trust to kind of sign off on messages and basically kind of execute the actions that are received from the source chain on the destination chain. There are a lot of these. If we look at them, kind of the ones that we're going to focus on a little bit today are kind of like Anyswap, Wormhole, Thorchain. But these are kind of predominantly the types of bridges that you see out in the wild. Usually any type of project which implements them also kind of caveats and says that like, okay, like we're doing this to get started just to kind of bootstrap liquidity or the ability to communicate between bridges, but we are looking to move towards a more decentralized model. After that, we have light clients and relays. These are more secure because the way they work is they kind of use cryptographic proofs in order to kind of prove the validity of the messages that are coming through. They have better security models. They're harder to implement because you need to kind of have clients on both ends, on source and destination chain, which are basically provers and prove that the incoming messages are indeed valid. We have liquidity networks. These are actually, in my opinion, some of the safest type of bridges, but they come with also their drawbacks, which is like suboptimal capital efficiency, because in kind of these cases, we're not kind of reproducing synthetic assets. You usually get the native asset on that type of chain. So let's dive deeper. Validators and federations. So this is like kind of the Wormhole model or any of the kind of like the larger bridges that you're likely familiar with. And kind of the flow is simple. You start off at the source bridge, you lock and mint your tokens. So let's say we're bridging Solana and Ethereum. Let's say we want to port our Ethereum over to Solana. So we go to some smart contract, which is like, we'll call it the client on the source. We'll lock our Ethereum. Some kind of relayer or some type of external actor will kind of dispatch that message on the destination chain. It will be received. Say, all right, we've seen that you've locked like your Ethereum within our Ethereum kind of smart contract. And for that, we're going to mint kind of the same wrapped asset on Solana. So you have wrapped ETH on Solana. When you want to transport the way back, you burn the wrapped ETH, which is a synthetic asset that lives on the Solana blockchain. And then the Ethereum blockchain, with the help of external actors, receives that message, says, okay, I actually see that you've locked the synthetic asset, which we've produced on the Solana chain. And now I'm going to kind of release your native ETH back to you in this case. And we have a lot of kind of applications that work with this. So Wormhole, Anyswap, Thorchain, and more. Wormhole has recently been in the news. We're going to touch and dive deeper into this when we look at the recent exploit that happened over the past 2 weeks. Same goes for Thorchain and others. Now, like clients and relays, like we said before, these use kind of headers of blocks and provers on the source kind of on the destination chain in order to prove the validity of the message that's received. It's a talk within itself, so we'll kind of stay high level here. But basically, you have these external actors to each of the blockchains that monitor events on the source and relay them to the destination chain. The destination chain receives events, uses a prover to confirm the validity of the received message. And if it's valid, it's going to kind of execute actions on behalf of the user on the source chain. A really kind of simple and probably most popular example of this is kind of minting assets on the chain. So we'll get more into that, and kind of popular examples for this are TBTC, the Rainbow Bridge, which we mentioned before, between Near and Ethereum. If we're going to dive a little bit deeper into the architecture, what we see here is the following. So like we said, with light clients and relays, each of the chain needs to implement basically a client that can monitor and receive messages. So on the Ethereum side, we see that there's a Near light client. On the Near side, we see that there's an Ethereum light client. We have also these external actors, which are kind of responsible for kind of data liveness, like monitoring messages that are happening and transporting them to the corresponding bridges. So let's say we want to kind of port our ETH over to Near. So basically, we'll deposit our Ethereum in a smart contract on the Ethereum blockchain. The Near Light client or an actor on the Near Light client kind of will see this, transport the message. It will kind of reach Near the Near protocol Light client. It'll say, hey, I see that actually your Ethereum here is locked and this is valid. I've used a prover to kind of validate that this has happened. And now I'm going to mint basically wrapped ETH on Near for you. So again, kind of the same model of synthetic assets being minted on corresponding blockchains. It's just the way that we do it is different. Now, liquidity networks, this is a little bit like out of scope for today, but they're actually very promising. We believe that they mitigate a lot of kind of the risk on the user end, but basically you need real liquidity on both sides of the chain. Here, we're not minting synthetic assets. You actually get the native asset in kind of the corresponding bridge. What that means is that somebody needs to provide that liquidity on the other end. So there are LPs on basically corresponding sides. It's secure because securing kind of the perspective that for users, if something happens to the bridge, you're not completely wrecked because you have, after you've basically received the native asset on the corresponding chain, because you have the asset. So theoretically, you haven't lost everything. It's not some synthetic asset which can be burned in a way that is out of your control. And that provides some type of security and assurance for users who are doing it. They just need to kind of pass the initial kind of swap between chains. Again, because it requires capital on both sides, real capital, and we're not making kind of representations of the assets in the form of synthetic assets, it's the least capital efficient. All right, so now before we kind of lastly talk about kind of how to model and solve for the risk that's involved in building cross-chain bridges, let's kind of look at some of the exploits we've seen over the past year and try to understand where they came from. So one example is Thorchain, which has been exploited twice, I think, over the past year. And kind of like these attacks, some of them are kind of really, really nice in the sense that they were complex and non-trivial, but they all kind of have the same root cause, which is bugs in implementation. Now, what we're going to focus on here, just because it's kind of the most recent, is kind of recent exploits, but ones that are happening in bridges which use external validators and federations. So we're looking at these types of bridges, or we're looking specifically at the Thorchain hack. Without going too much into detail, we have kind of these components, which we're going to touch on in kind of the components of the bridge. If we're modeling the architecture, you have two clients which sit on each end of the bridge, and you have the bridge itself, which is responsible for basically passing the messages back and forth. And what we see kind of as a pattern is that basically kind of exploiting the bridge itself or kind of corrupting the message is quite difficult. And most of the exploits actually originate in the implementation of the clients themselves. So in this case, in Thorchain, they were using basically an unsafe function. It wasn't safeguarded. The attacker basically saw the opportunity here, kind of wrapped Thorchain's implementation in their own smart contract, and was able to kind of call, basically be able to create these fraudulent messages and make away with tokens. Now with Wormhole, this one was like much bigger. I think kind of collectively, the amount lost over two of the hacks was less than 20 million in Thorchain. This one was freaking massive, all over the news. If I'm not mistaken, it's about $250 million worth of funds that were lost. Thankfully, users were made whole by Jump Capital. Let's understand what actually happened here. So again here, this is another type of bridge, which, if you remember, we mentioned earlier, which is of the type of external validators and federations. We have these kind of trusted actors which sign off on received messages and execute kind of actions on the source and destination chain on behalf of users. And here again, we have these three components, which is two clients on each end of the bridge and the kind of the bridge itself, or the channel for communication. Again, the bridge itself here wasn't exploited. It was the client that was acting on behalf of users. In this case, the Solana client. So let's understand what happened here. Basically, the kind of the Solana client wasn't checking who was signing who was signing kind of these actions, and the user was able to kind of emulate a trusted kind of guardian in this case, and this is what led to kind of the hack itself, which was in this case infinite minting. So let's dive a bit deeper into the code. This is kind of the implementation of the Solana client here. You don't need to know Rust too well in order to understand what's happening here, but this function is a verify signature function. And what's really important here to notice is that there's this kind of line here, instruction sysvar account info. Now, this is actually used, kind of delegates to an internal kind of Rust function that we can see here on the bottom. And unfortunately, kind of the implementation that was selected was using kind of a deprecated version of this function, which doesn't check the sysvar account address properly. What's actually crazy about this is that the team behind Wormhole knew this. There was a PR out to fix this and actually used the correct implementation, but it wasn't merged in time. And kind of the operating kind of theory here is that the attacker was monitoring the repo, saw this, and this was kind of the original inspiration for the attack itself. So this is just some kind of screenshots of if you're using SolScan, you can really see here when the attacker was basically able to exploit the fact that sysvar account addresses were not being checked properly, and basically infinitely mint synthetic Ethereum on the Solana blockchain. And you can see his account balance kind of before and after, which is quite staggering. So here, 120,000 worth of Ethereum. And then the bridge worked. So again, this wasn't a problem with the bridge, it was a problem in the Solana client. So he was able to bridge a lot of that back to the Ethereum kind of blockchain. Kind of anecdotally, like a bounty, basically there's a white hat bounty was offered to him to return it. As far as I know, he hasn't returned it yet. Jump has provided the capital to kind of back the Ethereum 1-to-1. So users in this case are okay. But again, this is another case of client implementation error. So now that we kind of understand different type of bridge architectures, we've even seen a few exploits in recent news. Let's talk about how do we model risk for cross-chain bridges. So, I won't get into the flame wars of which bridges are better than the others, and every bridge has its trade-offs, every bridge has its benefits, and kind of we're not prescribing which bridge to use. But we are going to say this, because of the different architectures and different bridges, there's no silver bullet, right? So there's no like kind of catch-all, one size fits all solution here, which we can recommend that will kind of guarantee automatically that your bridge is secure. It's important to understand what architecture you've selected and what the trade-offs and pros and cons are of that architecture. So this is a long-winded way of saying there's no silver bullet. Because this has been in the news and like currently they're the most prevalent type of bridges, let's focus on external validators, bridges that use kind of the model of external validators and federation. So in the attacks that we just saw, and generally speaking, corrupting the actual bridge communication is difficult. Usually attackers need to overcome chain consensus on either one or two of the bridges that they're trying to attack. This can be really expensive, really difficult, and just not economically like a good idea or feasible. So what we see here is attackers focusing, usually looking for kind of bugs or ways to exploit the clients themselves. So like we said before, we're looking at this architecture, 2 clients, 1 bridge in between, and kind of the focus here is on the edge clients. Once they receive a message, you have an incredible amount of power. In the Solana kind of Wormhole bridge, its ability to kind of mint synthetic tokens, which certainly have value. And this makes it a great target for hackers to kind of look at and be patient with. So what's the solution? So what we do at Chaos is we focus on continuous testing. So before you're going to roll anything into production, we're going to define a suite of kind of test cases that you're going to want to have. And these range from kind of black swan events. For different bridges, this means different things, but it could be very heavy network traffic, like very high latency on transactions, just really massive sums being transported back and forth, and seeing how that may affect kind of downstream things in your application. We run network simulations as well. So kind of the underlying kind of belief of how we operate here is we're not running these kind of like simulations in a pristine lab environment. We're literally forking all the blockchains that we're kind of testing. So in this case, the source and destination chain. We'll recreate kind of the bridge within kind of the context of the simulation. And we're going to run the bridge, and we're going to run messages and transactions through both blockchains in the same exact way, with the same exact interfaces that it's going to be seen later in production. Lastly, this is just generally good practice. You want to do some type of fuzzing. So there's kind of a finite amount of inputs that we can be creative with. We can randomly generate input into the basically all of the kind of public interfaces of both clients on both source and destination, and try to catch things with a wider net. So kind of, again, the list is much longer, but for brevity, the kind of the things that we simulate is recovery from failure, latency and communication errors, protecting your public interfaces. So what are the interfaces and methods that kind of can be called by anyone? Those are the ones that we need to focus on heavily. Fuzzing and randomization, which we just explained, which is basically spamming all of these public interfaces with different types of input to see what breaks. All right. So this is the call to action. If you're building a bridge, or if you're a layer 1 or layer 2 that wants to have a bridge on the protocol, and you value security and reliability, reach out to us. This is what we do. We're happy to help. We're happy to kind of plan with you the best way to secure these bridges for your users and your wider ecosystem. A little bit about the team. So we have deep tech backgrounds. We've all written mission critical software that has served kind of billions of people in different contexts. The team hails from Israeli cyber intelligence units, Facebook, Apple, Microsoft, and so on and so forth. And this is kind of what we live and breathe. So we're happy to speak. Unfortunately, this is a recorded session, so I won't stop for Q&A because it's likely going to be boring, considering that I'm alone here in an Airbnb. But this is my Twitter handle, Omer A. Goldberg. Feel free to reach out. DMs are open. I'm always happy to chat more about security, infrastructure, testing. Thank you guys. Enjoy Denver. And yeah, thanks for having me.